Hello, my name is Ian Workman. I will be presenting the intro and background of our project today, the robotic arm controlled through electromyographic sensing, also known as RACEMGs. Joining in the presentation today is my group partners who will be presenting as follows. For the requirements and specifications, we'll have Aboubacar Conde will be presenting. For design, Jeffry Lazo will be presenting. For integration and test results, Kyle Anderson will be presenting. And for the conclusion, Samuel Jimenez will be presenting. And I, Ian Workman, shall be presenting for the intro in the background. First, I will be presenting the intro and background. First, we have just the name. From it, we can get a general idea of what this project is and what we're trying to do. Robotic arm controlled through electromyographic sensing. So a robotic arm, which you'll see later in the presentation, made through the printing of, through 3D printing, and then controlled through motors. While all of this specifically is looking at being controlled by the EMGs, which are sensors that read the muscle actions, read the movement of your muscles, and will give us a signal which we use to control the robotic arm. So the original idea behind this, of course, is the commonly thought of is body-controlled robotics, specifically for additions to amputees or individuals who do not have the standard array and set of limbs. This was the original idea going into it. Unfortunately, with the issues of that specific application of the technology, there is a list of things that we couldn't necessarily get over. First being volunteers. We don't exactly have the array of individuals to test this kind of technology on, or the funding or access to try to find individuals and compensate them. Second of all, the scope of it. Research has gone very much long time for optimizing and creating these things, of which for a one-year project such as ours, creating it of our own, we don't exactly have the time or the resources to specifically go into that scope. Thus, the third point is the resources of doing that. It's usually a lot more expensive technology, of which we do not have the fundings. This project didn't specifically have the fundings to do such. And then following from that, the pre-existing work, as I said before, there's already a lot of research into this specific application of body-controlled robotics. And lastly, usually for amputees and stuff, there may be some invasive technology that has to be involved, which we do not want to personally get involved with for medical reasons and the such. Possible solution to each of these, or at least the target goal for what we're looking at creating to overcome these, is something that's a little bit more general and volunteer. So someone that even we could test on ourselves, smaller scope, something that's a little bit easier, make it cheap, something that is, like the smaller scope makes it easier, makes it cheaper, something that could probably be mass produced and mass used. Therefore, maybe looking for a different application rather than just for robotic controlled limbs for amputees or those not born with them. And then lastly, try to find something that's surface level tech. That way we don't have to go into invasive technologies. And this ultimately got me thinking about construction workers and industrial work, specifically being able to control machines using your own muscles. As we know from the title of this project, we ended up using EMGs. This is a form of usually non-invasive. There are some forms that tend to be invasive, but there's a lot of on-market, very cheap, non-invasive forms of EMGs out there, which we're going to use for this project. And for the application, I came up to the idea of using construction work and construction industrial work because of the fact that the workers within those areas would most likely have would most likely have all their limbs due to the requirements of the job. And from there, I wanted to see exactly how useful this application would be if being able to control these giant machines using your body muscles. First of all, there might be a level of like intuition to it. It might be easier to move on, control things by basically having a semi one-to-one ratio. So if your arm does a thing, then the machine responds similar to it, makes it maybe a little bit more intuitive. And secondly, from the description I have on the slide, there is a lot of injuries and construction deaths resulting from on-site work, which due to, or according to the Bureau of Labor Statistics, has been 1,013 of the most recent report. And of course, these jobs include these dangers include falling from heights, exposure to dangerous substances, accidents involving heavy machinery, handling of heavy materials, and being struck by debris. One benefit that I could see from the EMGs is that it may enable an individual to be a little bit further away from the work site if you're able to connect it to some camera system. So you may be able to keep your worker off heights or keep them away from heavy construction and have this intuitive sense equipment to work with.
My name is Aboubacar Conde. I'm going to present for requirement and specification of the project. The goal of the project is to design and build a low-cost and lightweight prosthetic robotic arm using electromyography sensing. As noted in the background, the type of electromyography used is the non-invasive one. This choice was safer. However, it impacted the accuracy of the electrical signal being collected from the muscle. This is why we narrowed down our goal to a specific task: grasp and ungrasp of fingers in a 360 wrist rotation. Furthermore, we defined the user context as industrial, though we focused on relatively light loads handling. Let's remember, for this project, controlled motion is key. To combine better performance and low cost, we utilize an Arduino. Uno Omega would work. This to perform all data acquisition and analysis. 4 DS servo DC motors to control all motion of robotic arm. 3 EMG sensors to collect data from muscles activity. And 3 pressure sensors to be placed on the fingertips of the robotic arm. These sensors are to be used to avoid crushing objects that are being handled by the robotic arm. The main concern for the hardware configuration is establishing reliable connection between sensors and motors, as well as translating the rotational motion of the motor to a linear motion. For the software configuration, C++ is utilized for all communication between different components of the system. To keep our system safe, a supply voltage of 7 to 12 volts is okay, along with the maximum current being drawn to 520 milliamps. This means that a power supply should be able to deliver at most to our system 12 volts and 1 amp just to be on the safe side. The pressure sensors put restrictions on motors as finger comes in contact with objects, thus preventing the system from being damaged. Given the relatively low testing accomplished, no other ways have been set up to deal with errors other than performing hard reset of the entire system.
My name is Jeffrey, and I will be talking about the hardware and software design involved in this project. In terms of circuitry, we decided to work with an Arduino Uno R3 due to its low power consumption, its ability to interact with digital and analog sensors, and its low cost. This microcontroller is the brain of the robotic arm. It is in charge of data processing and decision-making operations. We also worked with Myers muscle sensors to obtain activity signals from target muscles, and Adafruit round force-sensitive resistors to control the delays in the program. Servo motors were selected due to their angular accuracy and high torque. This project also required the addition of a 1000 microfarad capacitor to reduce the flickering or instability on the servo motors, and some pull-up resistors to obtain meaningful data from Adafruit FSRs. The following schematic wiring hybrid diagram contains a complete description of the circuit. AC and DC signals are labeled, and their flow is specified with arrows. Each electrical component has information about their input and output voltages and currents. This circuit requires an external power supply of 6 volts at 1 amp in order to work as designed, but it can still function for light operations with another power supply producing 6 volts at 0.6 amps. It is important to highlight that the highest the weight attached to the servo motors, the highest its current demand will be. Besides that, this circuit can also work with other microcontrollers from the Arduino family, such as the Arduino Mega 2560, which we recommend for future improvement on the hardware. This microcontroller allows the usage of more analog sensors, and it can handle more servo motors without the addition of a servo shield. In terms of software, the Arduino Uno R3 was mainly programmed through the combination between C and C++. This microcontroller can also be programmed using Python, but this method requires a few additional steps, and Python programs have a lower execution time than their counterparts in C. The main program was designed using an object-oriented programming approach, since it makes code simpler and reusable. This approach also allows the generation of future libraries, since header files and CPP files are a restructured version of the code defining the class. For this project, we aimed to use less than 30% of both program memory and data memory. For us, it was very important to develop a portable program. One of the goals of our project is to convert this class into library in the future. Hence, it is very important that the program provides other developers with enough space to continue developing the class or the library without running out of space. Our decided program requirements is 15% of both memories, which we were able to achieve. Now, Kyle is going to continue.
Now I'm going to be talking about integration and test results. So data was collected using the EMG sensors and the Arduino IDE software to collect and observe data. It was really easy to use because we were already using one of their boards, and it allowed us to receive data in real time. We had some issues regarding the signals we were receiving because a grasp motion or closing the hand and an ungrasping motion yielded the same values. The motors would not be able to differentiate between the two signals. The EMG sensors also needed to be put in specific spots for them to target the muscle groups we wanted. The Arduino software was used when testing the sensors. We were able to see a live feed of the signal, which helped the person using the EMG sensors see the responses of their muscles. We wanted to see what the signal would look like if there's no input from the muscles. So as you can see the graph here, the y-axis is an arbitrary scale which could be mapped differently using code, and the x-axis was just time. For this instance, a no input gave approximately 15 or 16. Along the way, we ran into some problems with acquiring the signal. On the graph, the higher number represented a stronger signal and a lower number represented a weaker signal. The sensors weren't differentiating between a grasping motion and an ungrasping motion, so closing and opening the hand. It was a major issue because we wanted the grasping motion to show a peak and an ungrasping motion to show a decreasing value as opposed to just another peak. So here we can see that they're the same. They look, they have pretty much the same value. So the motor is going to have a lot of trouble distinguishing between the two. The hand isn't going to work properly because the motor works based off of the signal received. We came up with two ideas to fix the problem. The first was to edit the code to pick up on the peaks of the signals and alternate between grasping and ungrasping. This would not only involve a significant amount of coding and testing, but it would also limit the ability of the hand. So the user could only grip and ungrip fully and alternate between the two. It couldn't do anything in the middle range, and it would reduce the fluidity of the hand that we wanted. So in order to not sacrifice functionality, we researched equipment that could help us with the situation. We found longer leads for the inputs that would distinguish the signal better. The only downside was that it would increase the cost of the arm, but it was such a small amount compared to the other parts we used. It would only minutely affect the overall cost of the arm, so we went with longer leads. Here we have pictures of the old leads and the new leads. The EMG sensor is pictured on the left. The inputs are from the two medical pads on, and then the ground is the third pad on the right, connected to the black wire. As you can see, the two inputs are really close together, so they couldn't get the full span of the muscle to receive the signal we wanted when ungrasping. The picture on the right shows the new leads we got, and the input points are far apart, giving the sensor more room to read the muscle impulses more accurately. The new leads also made it easier to work with the EMG sensors and put them in different locations with ease. So it just made testing really, really easy. After successful uses with the new leads, we can see some of the data on the right. The grasping yielded a peak, and with the graph, the muscle activation increases the signal. So naturally, the act of ungrasping should decrease the signal because you're putting less strength of the signal from the muscle, and a totally relaxed hand produces a low signal. The motor would respond to the signal as followed. As the signal increases, the motor angle increases, and when the signal decreases, the motor angle also decreases. So we set the motor angle to be 0 in a relaxed neutral state of the hand, and as the angle increased, the motor would pull the fingers down for a grasp, like a closing hand motion, and vice versa. The next steps of the project is to 3D print the hand we were designing and integrate the motors, Arduino board, and sensors that we have in our schematic. The other accessories that aren't shown that we are going to be using after it's printed is fishing wire and stretchy wires that go in through holes in the fingers that manipulate them from the motors.
My name is Samuel Jimenez, and I will be concluding this presentation. I'll be starting off by going over some key observations and insights that we gained. Scope of the project. It's important to define your scope. We wanted to develop a cheap, non-invasive platform for construction sites by providing a product that keeps operators out of harm's way. This involves preventing injuries and possible death from falling, exposure to dangerous substances, accidents involving heavy machinery, handling of heavy materials, and being struck by debris. Now, how do we do this? Having a well-defined scope for a project is very important in keeping its momentum. The amount of literature that goes into developing an idea is just as important as the execution, and that all starts with a pen and a paper. Finding balance, time and budget versus functionality. Solutions to engineering problems can be easily solved when budgets are not taken into account. Being able to develop a solution with low-cost materials is what sets apart other solutions from ours. Many times we're presented with situations where a decision between time, budget, or functionality had to be made. This is why having a clear scope of a project's expectations is key. This keeps you on task. Review and defects. As a project develops, there are areas where an idea may become over-engineered or even left over when an alternative solution is found. Having internal reviews is important to trim off aspects of a project that are not needed or do not need to reside within the original scope. This is crucial in keeping a project compact, organized, and agile. You will always run into unforeseen limitations, whether it be hardware or software. Contingency plans and having an alternative approach also keeps the project's momentum from being affected. I'll be going over some improvements and future work that can be made on our current project. First, I'll be covering signal processing. Being able to accurately distinguish when the hand is grasped and open is very important in how the hand is operated. If we're not able to accurately distinguish between a closed hand and an open hand, it makes it very hard for us to provide such a product that removes the operator from the construction site. Now, here's a few things that we would try to implement to make this possible. A huge part of this would be developing some wireless integration. Having an operator that is outside of the construction site, but still having the functionality as if he was there, keeps not only the operator safe, but can also reduce costs and increase the amount of available operators that can step into the site when one has to leave. Another way we want to improve on our project is sensors. If we can increase the amount of sensors, locations, and placements on the arm, we can define our signal a lot better and create more protocols for when the hand is closed, rotating, or opening. By continuing to develop the sensor locations, the amount, and placement, we would be able to also include sensors on different parts of the body for more applications. One huge aspect of our project that we would like to improve on is security. As with any type of machinery and robotics and communication signals, having a good security on your system that cannot be infiltrated is super important. And this is definitely a part of our project that we did not overlook. Some upgrades to our hardware that would help with the overall functionality would be microcontrollers and sensors. Replacing our microcontrollers with one would definitely help in streamlining our product. A final upgrade would be sensors. The amount of sensors and the quality of the sensors. Receiving more feedback from the user and environment would definitely help product's functionality. Thank you for watching.